going to finish this out with problem 6. Problem 6 is of the same sort as the first one, except that, the last problem, except that this one is a minimization problem. But the technique is pretty much the same. So we're again going to start by looking at our list of constraints. Think of that as a system of linear inequalities. We're going to graph that system of linear inequalities. And then that will determine that feasible region. We'll find all of the corners of the feasible region, and we're guaranteed to be able to minimize z on one of those corners. So now we'll look at graphing this region. So let's start with that first inequality, that 3x minus y needs to be bigger than or equal to 12. So it looks to me like if you set y equal to 0, then x would have to be a 4. In order to obtain equality there. And notice again that all of these inequalities are non-strict. That's going to be typical in linear programming problems. So most of the time we're going to have these non-strict inequalities and we'll be able to include the boundary lines. So we won't have to worry so much about dotted lines here. Now for the second one, this is a little bit odd because here we have a negative y is supposed to equal 12 if you set x equal to 0. So I sort of suspect that this is a typo. And in fact, I'm just going to change this to a positive sign rather than a minus sign because negative 12 for y would be way down here. So let's just pretend that's a plus sign. So in that case, if x is 0, then y would have to be 12. So that would live up here. So we're looking at that boundary line. And again, let's start by just graphing all of the boundary lines and then we'll figure out the feasible region. So next we'll look at x plus y is supposed to be smaller than or equal to 15. So for both of these intercepts, we would get 15. So we'll either have 15 comma 0, which would be way over here, or we'll have 0 comma 15. That would be way up here. Actually, let me clean this up a little bit. There we go. So we get this. So that's our second boundary line. And we aren't quite done with these non-trivial ones because we next have the boundary x needs to be bigger than or equal to 2. So saying that x needs to equal 2, that would be the vertical line at x equals 2. So this is another boundary line. And similarly, if we say that y needs to be bigger than or equal to 0, then we're looking at a boundary line of y equals 0, which is just the it's just the x-axis. So this is what we get as our boundary lines. Now we need to determine the feasible region. So we can pick any point here. What I like to do is if one of your inequalities is one of these axes, if one of your boundary lines is one of these axes, I normally like to ignore that one for now. It's clear that if you want y to be bigger than or equal to 0, you're looking at just the region above this graph, this line. So I'm going to omit that one for now, and that allows us to use as our test point the origin again. So I just prefer to do that because then it tends to be pretty clear which side of the boundary lines needs to be shaded. So we'll look at our first inequality here. Now I'll plug in the origin into this first inequality. Remember that this was our first line. So if I plug in the origin into that first inequality, I would get 0 is supposed to be bigger than 12. That's false. So the origin does not belong in the solution set for this first line, and that means that our solution set would be over here to the right of that first line. Next, if I plug in the origin into the second inequality, I would get 0 is smaller than 15. That's a true statement. So that means that the origin does belong in the solution set, and the solution set for that second inequality would be everything beneath this outer line. Next, you're looking at x values that need to be bigger than 2. That would be to the right of 2. So you're looking at everything to the right of this line. And similarly, if you want y to be bigger than or equal to 0, lastly, I'll add in this last boundary line. You're looking at everything above the x-axis. And the only region that all of these have in common is this region. And again, you might just guess this region based on the fact that this is the region that's bounded by all four of those lines. But this is what's called the feasible region. So we've now found the feasible region. Now we need to decide what the corner points are. And we know a lot of the corner points. Well, I guess we only know 2 of the corner points, actually. But let's figure out how to find the other corner points. So we know this corner point and we know this corner point. It looks to me like there are 2 other corner points. So maybe let me do this in a different color. So let's do this in red. So we have this corner point and this corner point. Those are corner points whose coordinates we've already figured out. So we know that this corner point is 4, 0, and we know that this corner point is 15, 0, because those are points that we actually used to plot the lines. However, in this case, there are 2 corner points whose coordinates we haven't met yet. So how can we find those coordinates? Well, one thing is that notice that both of these corner points are part of this line. And that line has the equation, whoops, that is not what I meant to do, but that's fine. So that line has the equation x equals 2. So we know that these corner points are at the intersection of these boundary lines, this boundary line and this boundary line, with the line x equals 2. So in order to find the coordinates of each of these corner points, all that we have to do is substitute x equals 2 into each of the boundary lines that we found already. So for example, if we plug in x equals 2 into that first boundary line, then what we would get is a 3 times 2 plus y equals 12. And that would be a 6 plus y equals 12, which means that y equals 6. So this one down here would be at the location 0, 6. And we can do something similar for the other. So if we plug in x equals 2 into the second boundary line, which was x plus y equals 15, then we would get, we would get 2 plus y equals 15, which means that y is equal to 13. So this line up here, this point up here has the location, oh, sorry, I've been saying 0, comma. These are not, oh no. The x-coordinate here was not 0, it was 2. Sorry about that. So this corner point happens at 2, 6, because remember our x-coordinate here is 2, and then similarly this one happens at 2, 13. And now we've identified our 4 boundary points. A boundary point, or rather I should say a corner point, always occurs at the intersection of 2 boundary lines. So if we have 2 lines and a corresponding boundary point here, we can find the coordinates of that boundary point by just solving the simultaneous equations. Let's say you have a line that looks like this. So this is not a very accurate picture at all, but just to give you sort of an example. Let's say that you have these 2 lines and you wanted to know the corner point which lives at their intersection. The way that you could find the coordinates of that point would be to solve this system of equations. It would give you an x value and a y value that simultaneously satisfy both of those equations, and therefore it would be a point that lives on both lines. So that's what we can do in general whenever we have more complicated situations. However, in this particular case, one of our boundary lines was just x equals 2, which immediately gives us the x-coordinate. But we can do this more generally. So next, what we have to do is we have to take our boundary points, I keep calling them boundary points, sorry, our corner points, and make this table of corners and the corresponding optimization value. Well, maybe let me call it the objective value, because we normally call the thing that we're optimizing the objective function. So I'll call this the objective function value. And let me just record what the objective function is so that we don't have to keep scrolling up. So it was 2x plus y. So now we'll make a list of our corners. Our corners are 2, 13, 2, 6, 4, 0, and 15, 0. And now we'll find the corresponding objective function values. For the first one, what we would have is a 2x plus y, which would be a 4 plus 13, which is 17. For the second one, we would have a 2 times 2 plus 6, which is a 10. For the third one, we would have a 2 times 4 plus 0, which is 8. And then for the last one, we would have a 2 times 15 plus 0, which is 30. And we were trying to minimize this objective function. So it looks like the minimum occurs here at 8. And that minimum occurs at the point 4, 0. So I would say that z is minimized at 4, 0 with a minimum of 8. And that's the solution to that linear programming problem. So again, in the future, what we're going to do is we'll talk about how to solve these linear programming problems by using matrices rather than by using graphs. But I think it's good to understand what it is that we're doing graphically. We're essentially just looking at all of these corners and trying to decide which corner is going to give us the optimal value that we want, depending on whether we want to minimize or maximize that objective.